The thing that's the problem with star formation is that it is not very efficient. Only about 10% of all little protostars that start to clump together to form a star actually become a star. 90% of them get destroyed. Because you see these areas where you see this bright behind it, very bright, well, those are massive stars that are forming. And they're putting out a lot of radiation, and that radiation starts dispersing all of the gas and dust around it. So anything like this poor little thing right here, and this little tiny thing here, and this one up here, they may not make it because they will be torn apart by the radiation from the more massive star forming in their general vicinity. Here is the same image, more close up. You can see these beautiful carved out areas here. These poor little clumps here are never going to make it because this one's going to radiate away all those little protostars and they won't make it. You will notice here that there's a big difference in scale. This is the Carina Nebula. This is a close-up of one of those carved out areas of the nebula. And this one is the same thing but a different orientation with a different filter. Do not be deceived by the different images. If you're going to study the Carina Nebula, you need to go to APOD, Astronomy Picture of the Day, do a search for the Carina Nebula, and the most popular pictures will show up there, and they will look very different depending upon the wavelength that they have been imaged in, what observatory is collecting the photons of information, and some of them will look very, very different. I have fooled, it's not like I really set out to fool you, but there is no up and down out there, remember? So if I take something familiar and turn it upside down, don't be deceived. So look at these images in all orientations and look at them at different wavelengths, because every wavelength tells you a different process that's ongoing in that particular star, and they're all important. The other complex is the Rosette Nebula. Again, you can see here the little carved out areas where protostars are forming, and maybe stars are going to form right there. And with the Rosette Nebula, you see this big sort of empty looking spot in the middle, this big space. That's because this group of stars right here is sort of like is a group of stars that are only a few tens of millions of years old. And it's sort of like the Pleiades. It is a cluster of massive stars that all formed out of this nebula, and all the gas and dust in that region has been dispersed. We are going to focus this year on this line right here. This graphic is an illustration of stellar evolution, all stages of stellar evolution. We have been talking about the stellar nursery and protostars forming out of that stellar nursery. Well, once that little clump forms, and once it actually becomes a star, its entire evolutionary history is now pretty much a given fact. Because what happens to a star depends upon its initial mass once it actually becomes a star. So what I have done for you this year, I'm concentrating on type 1a supernova events. I'm focusing on this one line of stellar evolution, so you do not have to worry about all of that other stuff. I took it out. Now I know you may be disappointed. You may want to do black holes and pulsars and neutron stars and those huge collapsing masses of stars, but for this next year, that's beyond the limit of the Federation. There be Borg, Klingons, Cardassians. You cannot go there. Okay. Now, if you're still participating in this event next year, you'll have your chance. I will extend the borders of the Federation, okay? But for this year, we are focusing right here on this particular line. Trust me, there's a lot of fascinating, interesting, awesome things taking place here too. Okay, I will be talking about the main sequence a lot and different branches of the Hertzsprung-Russell diagram, the HR diagram, which is a plot of temperature and luminosity of a star. And it's sort of like the periodic table of the elements. I call the HR diagram the periodic table of the stars. If you take chemistry, if you understand the periodic table, you know everything there is to know about any element, any atom. Somebody can discover some hitherto unknown element, place it on the periodic table, and you instantly know everything you need to know about it. You know its mass, its radius, you know how many energy levels it has, you know how many electrons in its outermost one, you know if it wants to give away electrons, if it wants to take in electrons, if it wants what kind of a bond it's going to form, covalent or ionic, you know if it's a metal or a non-metal, you know everything. So, the HR diagram is the exact same thing. If you plot the temperature and the luminosity of stars, those two physical properties, and when I say luminosity, you can also say, or substitute, because it's the same thing, in a way, the absolute magnitude. Because there is a relationship between the luminosity and the magnitude, and these are all, the luminosity is based upon the sun. One luminosity is one solar luminosity, how luminous our sun is, and everything else is relative to that, either more or less luminous. So the sun, if you plot it on the HR diagram, it's plotted right here on the main sequence because it is obviously one solar luminosity and it's about a G2 stellar classification star. One thing I will tell you about this diagram is it is a cartoon, a gross cartoon of the HR diagram. As with everything else in life, it's really much more complicated than that. There are many more classes than OBA, FGKM. Okay, but for simplicity's sake, we just go with a few basic ones. Absolute magnitude is how bright it is, and again, like chemistry with the pH scale, this is a logarithmic scale, and which the sun, if you lined all the stars in the sky up the same distance away of 10 parsecs, then our sun would be about a +5. Now, when you go out in the night sky and look up, you can see as faint as +6. And that's about it. So the sun is not a very bright star overall. And the more luminous ones go up to -10. Some events, of course, supernova events are more brighter than that. So the higher the negative number, the brighter it is. The higher the positive number, the dimmer it is. So down here we have hot and dim, hot and bright, cool and bright, cool and dim.